All right, so first you were supposed to figure this out however you wanted. Here's the problem. One tree starts at 4 feet tall, grows 2 feet per year. Another tree starts at 7 feet tall and grows 1 foot per year. After how many years will they be the same height, and what height will they be? So you had a few options about how you could figure this out. Some of you might have chosen to do it in your head. Some of you might have chosen to do something like this, like a table. This is like the year, and then this is tree number 1 and tree number 2, right? A table would have been a great strategy to use. Like, so here's like they start something like this. Okay, so like tree number 1, right, starts at 4 feet tall, and it grows 2 feet per year. So after a year, it's 6 feet, and then it's 8 feet, and then it's 10 feet, and then it's 12 feet, and so on. And I might have to make the table longer, we'll see. Another tree starts at 7 feet tall in year 0, and it grows 1 foot per year, 8, 9, 10, 11. And I would have noticed that after 3 years, they are both 10 feet tall. Okay, now you might have had a different strategy. You might have done some of this in your head. That's fine. You could have also chosen to say, you know what, I'm going to write an equation for this. My starting point is 4. That's my B. Right? That's my B. And my rate of change is 2. It's changing by 2 feet per year. So you might have written an equation for that one and an equation for this one. And you could have actually used substitution to solve, right? It would have looked like this. You would have subtracted 1x from both sides. And oops, this is x plus 4 equals 7. And you would have gotten x equals 3, that's the number of years, and you would have plugged back in here and you'd have gotten 10. Okay, so any method that you chose here is fine. But what we're going to start looking at is problems that really you can't solve with a table. Like, let's say, for example, you had made a table, but then the numbers weren't the same, right? Like, maybe you'd have had to make a table up to 50. Maybe they weren't going to be the same height until 50 years. You don't want to make a table. We want a better strategy. So we are going to learn how to do this, right, with lots of different situations. So here's what it looks like. When you get a word problem, the first thing you're going to do is you're going to define variables, okay? Define variables. Variables are things that change. Like, for example, here, the number of years changes, right? The years pass, and it's like, oh, it's been 1 year. Oh, it's been 2 years. Oh, it's been 3 years. That number changes. And the height changes too, right? This height is changing over time, okay? The height of the tree is changing. So sometimes variables are things that change. Sometimes variables are things that don't change, but they are unknown. And we're trying to figure out what they are, right? So for example, like the price of something or the number of a certain animal, right? Those aren't things that change, but they might be unknown. And what I'm going to tell you to do is choose logical letters. So for example, here I used y and x, right? But what would have made more sense is for me to say, okay, I'm going to use years, I'm going to use y, right, for years, and I'm going to use h for height, right? So then that makes sense because at the end I would have ended up with like y equals 3. And I'm like, what equals 3? Oh yeah, y stands for years, right? And then, you know, the height I would have gotten 10, and I would have been able to kind of realize what those variables stand for. Once you have letters and you have decided what the variables are, you're going to write equations. You're going to ask yourself, what do I know about the variables? How are they related? Okay, and you're going to see this in our first example, and you're going to write those 2 equations. Now, once you have the 2 equations, you're going to use the best method to solve it. So you'll reference your notes on page 16, and you'll remember that if they're both in standard form, you'll use elimination to solve because that's the easiest. If they're both in slope-intercept form, you'll use substitution. Do we sometimes use graphs in this situation? Yes, but I'm not going to provide a graph, and I'm just going to tell you substitution is going to be your better option here. Same deal if there's one standard and one slope-intercept, you're going to use substitution. And what we can do is we can take a moment and flip back through the notes just so that you have the page numbers, right? So like, for example, substitution, you're going to want to look on page 8 and 9. And in fact, we can even be more specific. If one equation is in standard form and one equation has a variable isolated, that would be the notes on page 8. And if you have 2 equations in slope-intercept form, that would be on page 9. You can reference those notes. And let me get you page numbers for elimination, right? Because this is when you get your equations, you're going to want to be able to solve them. So this is going to be pages 12 through 14 is going to help you with elimination if you need those notes. Okay, once you solve, make sure you check your answer and ask yourself, when I check my answer, do these numbers work in the original problem? Does this make sense? And then go ahead and write your answer, right? You're not going to write your answer like this, right? Because the question is not going to ask for a point on a graph. It's going to ask for, some real life thing. So don't write your answer like this. Make sure that you're writing in a sentence. Okay, so we're going to use this method and we're going to try this first example.